Now that you've seen reaction of a halogen by itself with an alkene, I want you to consider what happens if we add a halogen, but we use a solvent that can be a nucleophile. So in this case, I'm adding Br2 to my alkene, but I'm using water here as my solvent. You might be wondering, what was the solvent in the previous case? In this previous case, probably we used a non-nucleophilic solvent, something like CCl4. That would be a non-nucleophilic solvent. So in that case, once we formed our bromonium ion, the only nucleophile available was the bromide ion. In this case, now I have an alternative nucleophile around, and you can see the result we get. So what I'd like you to do, refer back to your notes from the prior reaction and see if you can draw yourself a mechanism for this reaction. Pause the video and then come back once you've drawn your proposed mechanism. All right, so now that you're back, hopefully you were able to draw a first step that looked just like the first step we saw before to form the bromonium ion. We have essentially an attack of the alkene on Br2, and then we have what I like to think of as a counterattack of the lone pair bromine on pi star Cc. That's going to form a bromonium ion. Now, one thing to think about here is stereochemistry. If you've done the stereochemistry module, then you might notice that this is an E alkene or a trans alkene. What that means is when I form my bromonium ion, there's a couple of different ways I could represent it. I think the best way to represent it would be to draw my three-membered ring in the plane of the page, because that triangle defines a plane. And my two methyl groups now, if one's coming out of the page, the other one would be going into the page. Some people will draw it this way, keep the chain as it is, and then draw my bromine, say, coming on a wedge from both of these. That representation is okay. The reason I don't prefer it is this carbon right here that I'm highlighting in purple, that doesn't look like a tetrahedral carbon when we represent it that way. Either one of these would be acceptable, though. So I've formed my bromonium ion, and now, even though I have Br minus around, since H2O is the solvent, what this means is there is lots of this present. So we've said before that high energy intermediates like a bromonium ion or a carbocation will react with the first nucleophile they see. So if H2O is the solvent, it's going to be much more likely that a molecule of water bumps into the bromonium ion before a bromide ion does. So my second step would involve a water molecule attacking the bromonium ion. Remember, it's attacking sigma star CBr. So we could attack here, break that CBr bond. What that's going to give me is now an intermediate that looks like this. My nucleophile, my OH2, is going to be across from where the bromine was. And so my next intermediate would look like this. You might notice that's close to the product, but I have a very acidic proton. Remember, when we have a very acidic proton and we need to remove it to get to the final product, we can just call on Sol to remove it. So that would give me this product. And if we're thinking about the stereochemistry of the product should looked like this, where one of these is a wedge and one of them is a dash. You could also make the bromine on a wedge and the OH on a dash. It would give the same stereochemical outcome. This is an anti-addition, just like the addition of Br2 was, where we saw only anti-addition. In this case, we're going to see only anti-addition as well. For this last step, I used Sol to deprotonate. It would also be okay to use a water molecule or to use a Br- ion. That would be fine. You might notice there's a byproduct here. In general, organic chemists are not great about balancing their chemical equations. If you're someone who really wants to balance your chemical equation, you might note that our byproducts here are H3O plus and Br minus. And we actually involved 2 water molecules in the reaction. So there would be 2 of these involved, one that adds in and one that deprotonates at the end. You could use bromine to deprotonate, and then your byproduct would be HBr. But if you remember, HBr is a strong acid. So in solution, it's more likely to exist as H3O plus and Br minus. But in general, it's okay to leave out the byproducts. That's something that you'll just become more and more comfortable with the more organic chemistry you do. So there, we've seen addition of halogen on its own, addition of halogen with water, and similar to module 16, we saw that anything we could do with water, we could probably do an analogous reaction with an alcohol instead. So what if I use Br2 with an alcohol instead of water as my solvent? Take a minute, draw yourself the product, and I think you can predict which of the 2 products we would expect to see here. So again, I would ask you to pause, go ahead, draw your mechanism, come back when you're done, and then check. All right, hopefully you've drawn your mechanism. And like I said, you want to practice these steps, even though you've seen them before, practice them until they become sort of part of your muscle memory. So your first step is going to be to form the bromonium ion. That would look something like this. Now that's going to react with whatever nucleophile it sees first. In this case, if I'm using an alcohol as my solvent, then that would be a molecule of alcohol that attacks the bromonium ion. Because it's attacking sigma star CBr, it's going to attack from opposite where the bromine is. That means it would give me the oxygen on a dash here. And then we would use Sol to come deprotonate. And that's going to give me this anti-addition product, not the syn addition. And that plus minus means I would get both enantiomers. So if we chose to attack the other carbon, then we would make the other enantiomer of that product, where bromine's going back into the page and OR is coming forward. All right, so those are different mechanisms that go through the bromonium ion, just like we did various examples where we went through a carbocation. We've done a few different examples where we go through a bromonium ion. One thing to consider we haven't considered yet is the question of what if I have an asymmetric alkene to start? So notice in each case here, I started with a symmetric alkene. What happens if we use an asymmetric alkene, where the two sides of the alkene are not the same? So in other words, this next example involves a tertiary carbon and a primary carbon. It turns out that this reaction is regioselective, just like reaction with HBr was regioselective. And it turns out it follows Markovnikov's rule. In other words, my more electronegative atom, my OH, that ends up bonded to the more substituted carbon. While my less electronegative atom bonds to the less substituted carbon. So that's a long-winded way to say this follows Markovnikov's rule. So let's think about this. In our mechanism, we said we would form a bromonium ion. So that first step is going to remain the same. We attack sigma star CBr, sigma star BRBR. We do a counterattack where the lone pair attacks pi star CC. We make ourselves a bromonium ion. But this is not a symmetric bromonium ion. And it turns out that water is choosing to attack one specific carbon. If we give our carbons numbers to keep track, 1, 2, 3, and 4. Here I have 1, 2, 3, and 4. We are attacking carbon 2 rather than attacking carbon 3, even though in theory we could attack either one. So the water molecule is going to attack carbon 2. That will give us an intermediate with a very acidic proton. In order to deprotonate, I'm going to call Sol. Another molecule of solvent will come and deprotonate that and produce my product. But the fact that the water is choosing only to attack carbon 2 and not carbon 3 tells us something about a bromonium ion. And while this is not exactly resonance in the way we usually think of it, we usually think of resonance as involving pi electrons, and there are no pi bonds here. We can imagine that the bromonium ion is sort of like a resonance-ish hybrid between two different things. I could imagine breaking this bond and making a carbocation on carbon 2. Or I could imagine breaking this bond and forming a carbocation on carbon 3. Right, so to keep track of our carbons again, 1, 2, 3, and 4. we can imagine that this is like a hybrid between these two carbocations. All right. And when I think about which of these two carbocations would be more stable, it would be the one on the left. So the way we rationalize this is to say, well, if that's the more stable resonance structure, this contributes more to the actual structure. So in other words, my actual hybrid structure, since it's not symmetric, is going to look more like this, where the bromine has a stronger bond to carbon 3 and a weaker bond to carbon 2. And so that makes carbon 2 a more electrophilic site. So the bottom line that I want you to take away is that when we have this bromonium ion, the more substituted carbon is the one that is more electrophilic. And we see this pattern across other functional groups that also have 3-membered rings with positive charge. We'll see one of those in a future module. So this is kind of a general trend that you'll expect to see. So when you attack a bromonium ion, generally you're going to attack the more substituted carbon if it's asymmetric. So given all that, I want you to think for a minute, pause, decide which of these 4 potential products you would expect to see when reacting this asymmetric alkene with Br2 and H2O. Pause and then come back once you've made your choice. All right, so the guiding principles here to make your choice, you want to consider the regiochemistry. We said that bromine would end up bonded to the less substituted carbon and oxygen to the more substituted carbon. That allows me to eliminate answers A and B because those have the wrong regiochemistry. And then stereochemistry, we said this would have anti-stereochemistry. So I could eliminate B and D on those grounds because those have syn stereochemistry. So that leaves me one correct choice, and that would be answer choice C. All right, so those are the reactions that go through halonium ions. You'll get some practice with those on the Skill Builder.